Okay, on to the second example. You'll notice these questions they're time consuming. They do take a little bit of time to work your way through. So that's why there's only like or I think there's 8 or 9 questions assigned for homework because it takes you that much time. So here's the second one. It's a rational function this time. So I'm going to still find my derivatives first. So I'm going to use the quotient rule here. All right, and it's going to look like that. Over the x squared plus 4 squared. I want to clean that up a little bit, make life a little bit easier for the next step. X squared plus 4 squared. So when I clean that up, I have negative x squared plus 4 over x squared plus 4 squared. And no, you cannot cancel those out, all right, because of the sign. So there's your first derivative. Now, second derivative, negative 2x, x squared plus 4 squared, minus negative x squared plus 4 times 2, and we'd end up with x squared plus 4 multiplied by 2x. So we use our chain rule there. All divided by x squared plus 4 squared. Now we look at this one, make life a little bit easier. There's an x squared plus 4 here, and there's an x squared plus 4 here. This one only has an exponent of 1, so I can cross that one out and cross my exponent out there, and then we're dividing it. Oops, that denominator. Hopefully someone's saying, why is the denominator not 4? Haha, it's going to mess it all up. I remembered. So when you cancel, you take one term out, you're factoring it out, that would drop down to an exponent of 3. So it makes it a little bit easier to simplify, because on top I just have a monomial times a binomial to multiply into. So negative 2x cubed minus 8x. The second term, it's really the same thing. I really have these two terms create a monomial. That's really just 4x. I'm going to distribute it in there. So we'd have become a positive, and it'll be 4x cubed. And then we'll have minus 16x. That's all over the x squared plus 4 cubed. Cleaning that up a little bit, we end up with 2x cubed minus 24x all over the x squared plus 4 cubed. So there is our first and second derivative. All right. Like I said, you can go wherever you want, so I'm just going to highlight those so I can find them a little bit easier. What's next? Let's do x-intercept. So x-intercept. So I'm going to let y equals 0. 0 equals x over x squared plus 4. Remember, this is basically letting the numerator equal to 0. All right. So we have an x-intercept at, and we can do a coordinate here. It'll be 0, and when I plug 0 into that equation, it's going to be 0, so it goes to the origin. All right, and then let's do a y-intercept. Since we're in that mode, let x equals 0, so your y-intercept would be at 0 over 0 plus 4, which is 0, so therefore y-intercept, same location. So it passes through the origin, this function. All right. Okay. Back up a little bit here. Let's do asymptotes now. So vertical asymptote. Oops, red. So it's the restrictions. So let denominator equals 0. So therefore, 0 equals x squared plus 4. X squared equals negative 4. Square root of negative 4. We'll go with inadmissible. So therefore, there's no vertical asymptote. Next, I move on to the horizontal asymptote. So that is g of x. What we're going to do is we're going to do the limit, as x approaches infinity for g of x. And the way you do that, you look for, this goes back to the unit 3, okay? You look for the largest exponent in that function, it's x squared. So it's going to be x over x squared over x squared over x squared plus 4 over x squared. I'll go down to 1 over x on top. Those guys would cancel out to create a 1. And we're going to say this is going to head to 0. 1 over x is going to go to 0. So therefore it's 0. So therefore we have a horizontal asymptote at y equals 0. So we have our asymptotes. Let's see what max min is going to look like. So max min, this is where we let the first derivative equal 0. So the first derivative is right there. The nice thing with this is that, again, because it's a rational function, you just let the numerator equal 0. Because you'd multiply that denominator up to 0, it'd be 0. So x squared equals 4. X will equal plus or minus 2. And 2 is a nice number to work with. So therefore, max min at, take 2 coordinates, 2, negative 2. So we'll plug it into the original equation. So if we put a 2 into the original equation, we would have on the bottom, we'd end up with 8. Yep, so 2 over 8. It's 2 over 8, that's a quarter. And if we put a negative 2 in, negative 2 squared gives us still 4. So it'd be negative 1/8, or sorry, negative 1 quarter. So there are 2 locations of max min. So you can see that actually you're going to find rational functions are a lot nicer to deal with. Let's find an inflection point. And if I have to find concavity, I will, but you've got so much experience graphing from last semester. I always say it's usually not worth. Concavity is usually figured out by then, but if necessary, we can go into detail with that. So 0 equals, and again, 2x cubed minus 24x over, and again, because it's a rational function, we just set the numerator equal to 0. That's all we're really looking for here. I'm going to factor out a 2x, which would leave me with x squared minus 12, which means that I will have 2x, and this is going to be x, well, maybe I don't want to get too fancy. That would mean x squared equals 12. X is equal to the square root of 12. So we have 3 inflection points. IP's at x equals 0. And then plus or minus root 12. And that we're going to have to kind of calculate or approximate. So we look for the nearest square root. So anyhow, we'll deal with this one thing at a time. So now what I always do now is I plot the information given. So I look at my x, y intercept. So that's going to be at 0, 0. And for this one, I think I'm going to go up by, maybe I'll go up by half. I know it's not a very large graph just by looking at the numbers. And then we'll go 1, 2, 3, and 4, negative 1, negative 2, negative 3, negative 4. So I know it goes through 0, 0.
Excuse the interruption. Please remain in your seats.
Okay, so now we're looking at the asymptotes here. So there's no vertical asymptote. There is a horizontal asymptote, and it's at y equals 0. So make sure you're using a dashed line to represent horizontal asymptote. So there's our horizontal asymptote, and it does head in both directions. I don't have a pink pen, so I'll just put that arrowhead on. Okay, so there's another piece of information added. All right, and now max min. 2 and positive 1/4, -2, -1/4. So I have 2 1/4. So that's going to be right about there. And -2 and -1/4 is right there. And do we have any other information? Oops, going the wrong way. So when we look at the rest of the information presented there, I have inflection points when it changes concavity. I know at 0 it changes. Now plus or minus root 12. So just remember that root 9 is 3, root 16 is 4, and 12 looks like the middle to me. So it's going to be about 3.5 approximately. So at 3.5, we have an inflection point. It changes concavity. So let's just go over and take a look and talk about that. So at positive 3.5, so right here in this region, it changes concavity. Well, you know that this is a max or a min. So I'm going to guess that this is a max. And the reason I'm guessing that is because its counterpart is below. So if it's a max and a min, they must be respectively max and min. So we are going to have some concave down here, and we're going to have concave up. So this is just from experience from your last course. We know that this point here is an inflection point in the middle, so that makes sense because we go from smiley face to frown in that region. Now, how does this end? Well, there's no other x-intercepts, okay? So that means that the rest of this graph will not cross the x-axis, which is also our our horizontal asymptote. So that means at 3.5, it's going to change to concave up, which means the curvature is going to change, and you almost have to, because if you didn't know about the inflection point, and I told you you have to draw this exiting with the horizontal asymptote, but you can't cross it, you would draw it, and the only way you can get it to exit is you got to bend it the other way to follow that horizontal asymptote. So the IP, oops, the IP will be in there somewhere. I know it was about 3.5. So there's our IP. Now, I can have you calculate it out. And my problem with this is the practicality, all right? Your cell phones can likely download a graphing calculator software. So rather than going through and finding all the information, what I ask students to do is I want you to show me enough information that will generate the correct graph, okay? So some people need to generate a little bit more information than others, all right? But for the most part, I just need enough information to prove to me that you come up with an accurate sketch. So there's our final graph. So did I have to go to the second derivative test to find concavity? Well, I know from experience there was a max and a min value that we got. When I plotted them, it becomes pretty obvious which one's the min and which one's the max. So that's inferred information. So I do like to see thinking skills involved here. So you are going to find that in the first note for this unit, I gave you tons and tons of tools to use, but do I use them for every example? Absolutely not. So basically I go through and I find what I can find or what's easy to find, and then I plot that information, and then I see if I have enough. If I don't have enough, and you're going to see in later examples, I'm going to have to go back and I'm going to have to find that extra information. But I'm pretty confident and comfortable with this, that I don't need to go any further. All right, so keep that in mind. I think I have 2 more examples to go through. I know they're time consuming and I do apologize, but it is important that you at least can come up with basic sketches. Like I said, the feedback at university is that it's an important skill. So we'll see you in example 3.